using data from yesterday, why the relationship between pressure and volume is considered inversely proportional.
Because volume was volume was decreasing. Like it started at a high number and then it started decreasing.
Okay.
Whereas pressure, it started low and then it started increasing by a lot.
Okay. So you got a graph that looks something like this, right? Like this. And we have pressure versus volume. These aren't our same numbers, but did everybody get a graph that looks something like this? So let's take a look at this graph and see what this is showing us. So, Fabian, you said I started here?
Yeah.
And I have or where did we start? Where was our starting point when we had our syringe?
50.
So we started over here. There's the point here. Okay, so we started here. And then what did we do?
The volume started going.
So we decreased the volume.
Yeah, 2, 4.
And then
it came to 30.
okay, so we went this way on the graph.
But then the pressure was increasing.
So as we decreased it, we saw that the pressure increased. So this shape or this relationship is what we call an inversely proportional relationship. As one increases, the other one decreases. Did we see any sort of relationship like this with our tanker? Did you see a relationship between, or your top can, a relationship between pressure and volume? Tell somebody next to you if we saw any pressure and volume changes in our pop can. A relationship between pressure and volume. Okay, so what did we see in our tanker or our pop can? A relationship between pressure and volume.
Different size of can.
Okay.
The amount of water is the same. Different crushing.
Okay, so you have the different sizes of cans. So which one is that? So this amount of space, the volume in the can was different for your different sizes of cans, and how did that relate to pressure?
By how much it crushed.
Okay, and what did you see?
The medium crushed the most, and the small one didn't crush as much, and the big one didn't crush as much.
Okay, and what was your thinking about why?
What?
Why did you think that? So maybe some people from your group can also contribute to this, but you had pressure, or how did that affect the pressure? You said you guys were thinking about these different sizes of cans, but you thought something about the pressure of those different sizes of cans. Let's say you have your big, tall can. What were you thinking about the pressure in that can? Why?
Because there is more space. Because of the amount of water we have, there wasn't that much pressure.
More volume, so less pressure.
Okay, and so that's kind of, if you increase the volume, you're decreasing the pressure. So that's what you're thinking for that. How about for the tanker? I heard a lot of you talking about the tanker. I heard you guys talking about it. What do you think, Peter?
When it was overnight, the thing decreased, the pressure inside decreased because it got cooler, so there's more space in it.
Okay, so overnight we had that sealed up tanker. So he's saying he knows that the temperature changed and that also changed the pressure inside, and that then we said that now there was kind of more space inside of that tanker. So there's a lot of variables going on in that situation, but we did see a difference in pressure and volume. When we were doing this yesterday, pressure and volume, we were keeping temperature the same the whole time. So sometimes there's like these intermixed relationships that we'll see between all these different variables, but with this graph, we're keeping temperature the same the whole time too. Okay, so here is another look at, so not using the data we collected, but on the second part of your activity, we're looking at a piston that was moving and it had the same volume of air, or it had the same amount of air inside that piston the whole time, and it was pushing in. And so it told you some measurements of pressure and it told you some measurements of volume, and you calculated these. You calculated pressure divided by volume and pressure times volume. And so what do we see from this? Which one, I mean, clearly we can see that when we divide pressure divided by volume, we don't get the same number, but when we multiply pressure times volume, this times this, we got 5. 6 times 0.83, we got 5. We see that this product of pressure times volume is always the same if you keep the same gas, the same amount of gas, and we're not changing the temperature. And so those two things together are what give us the gas law that's called Boyle's law. Okay, so Boyle's law is this idea that the pressure of a given amount of gas is indirectly proportional to the volume, and that's if we're keeping the temperature constant. So remember yesterday we started our notes here and we said we have these different variables that affect the behavior of gases. We have pressure and volume, and then we also have number of molecules and temperature. And we're looking at just pressure and volume. So if we're looking at just that relationship, we're going to assume that we're keeping the amount of gas the same and the temperature the same. And so then what you saw from this table is that if you keep pressure and volume the same, if you keep the amount of gas the same and the temperature the same, any change in pressure and volume will still always multiply out to be the same thing. And so that's what this law is telling you. That the initial pressure and the initial volume multiplied together will always equal the second pressure and the second volume multiplied together. It can also be written like this, but this one works pretty well. So if you remember, P1V1 equals P2V2. Pressure, initial pressure times the initial volume. So you're starting, whatever you start with, if you multiply those two together, should equal whatever, if you know the final pressure, you can calculate the final volume. Okay, so I want you to use that idea to do a quick practice problem, and then we'll sum up what we know about pressure and volume. So you have a balloon full of gas, and it is 7.5 liters, and it's a pressure of 1 atmosphere. So if you take that balloon underwater to a depth where its new volume now is 2.5 liters, I want you to answer these 3 questions. Talk about it with somebody next to you. Did the volume of the balloon increase or decrease as it went underwater? What do you predict will happen to the pressure? Will it increase or decrease? Explain. And what is the new pressure? So take about 3 minutes with, you can talk to the people around you, but you want to answer these 3 questions. So which ones of these do we know?
P1.
Okay, we know P1. What's our P1?
1.
1 what?
7.1.
1 atmosphere. And what's our V1?
7.5.
Okay. Do we know, which ones of these do we know?
V2.
We know V2. What's V2? This is the final volume of the balloon, so we know that. So we're solving for P2. So you know these things. This is your unknown. Okay, good. So go ahead and calculate that out. Using the equation. Did you get it? You guys got a number? Okay. So we have our initial pressure and our initial volume. So P1 is 1. So we said 1 atmosphere times 7.5 liters equals our second X times 2.5. So we have 7.5 equals 2.5 times X. You divided both by 2.5. And you got X equals 3. So 3 what? What is this 3?
3 atmospheres.
Okay, so we had 3 atmospheres. Does that match our, is that what you thought would happen with the pressure? You thought that the pressure would increase? Okay, so why did you think the pressure would increase? Okay,
As our
so
graph shows.
what?
As our graph shows.
Because as your graph shows, as the volume decreases, pressure increases. Good. Okay, so take out your notes section here in your journal. And we're going to fill in what we now know about the relationship between pressure and volume. Javier? What do you think is the relationship between volume and temperature? Let's say I have a balloon and it has a certain volume and it's in room temperature. And then let's say I take that balloon and I put it in the freezer. What's going to happen to the volume of that balloon? What? So why would it decrease? I put the balloon in the freezer.
Yeah, decrease. Wait.
Good.
Yes. Decrease.
Okay, why would it decrease? So you've done it before? Okay, so let's hear from someone over here. We have this balloon, we put it in the freezer. They're telling me it decreases in volume. Why would it decrease in volume?
Because it's cold.
Okay, and so what does that have to do with anything? Yeah, what do you think?
Molecules slow down.
Okay, the molecules slow down, and so why would that
Freezes.
decrease the pressure?
Because
It
there's
makes
no
all of them
pressure.
together.
There's no
I mean,
pressure.
why would it decrease the volume?
Because they don't need as much space to move around.
There's no pressure
Because-
putting up against
It's
the
not
balloon,
hot.
so it doesn't-
Because they
Yeah,
stop
The
moving
temperature
so
is
much.
decreasing, so the volume getting smaller.
Okay, so we have these molecules inside the balloon, they're moving around more slowly, and we see that volume.
Yeah.
You think the volume's going to decrease.
It's going to go back to a normal balloon that we know.
Okay, so we're going to look at that relationship today. We're going to fill in all of these exact same types of things for volume and temperature. So we're going to look at, guys, we're going to look at how, if they're proportional, if what happens if you increase or decrease one or the other, what the graph would look like, and what kind of equation we could have. A lot of you kind of probably have a picture in your head of what some of these things look like already. So to do that, first we need to quickly talk about one last thing, which is how we measure temperature. So we've talked already about measuring things in Fahrenheit or Celsius, but today we need to talk about one more temperature scale. Okay, so we're used to measuring things in Celsius, and if we take that balloon and we put it in the freezer, let's say we're started here like at 30 degrees, and then we put it in the freezer, it would go to right here. So we're at 0 for the temperature. So let's go back to this graph we had here. We have pressure versus volume in our syringe. Do you think that in our syringe yesterday, when you were pushing down on the syringe, what's the smallest volume you could get? So the smallest you could get it was at 10 yesterday. Do you think if we had something that was really, really, really putting lots and lots and lots of pressure on
We got
there,
it at 0.
could you get the volume all the way down to 0?
No.
Why not?
If it's at 0, then the pressure gets 0.
If it was at 0,
If it was at 0, the cap would pop
It would
off.
break before it got to 0.
okay, why would it break before we got to 0?
The whole thing would blow up.
There's more pressure inside.
It's- So we can't just get rid of pressure somehow.
Well, with magic.
Okay. But let's say we don't have magic. We have air trapped inside that syringe. And I don't still have it up here. Oh, I have one here. I have air trapped inside this syringe. So if I had like ultimate strength, could I ever get this down to 0? Why not? What's going on in here?
Not even if you're Superman.
Pressure.
But why is there pressure inside?
Because there's so many collisions between the molecules.
Hey, did you hear what Rika just said? What'd she say?
Collision.
Okay, listen please. So why?
Because there's so many collisions between the molecules.
There's so many collisions going on here. Can we ever get this all the way down to 0?
No.
Okay, we can approach it.
Did you let go of your finger?
Yeah, if I let go of my finger, then I'm letting out. When I let go of my finger, I'm letting
The pressure.
air out.
Okay.
But if I keep that air trapped in there, we have so many collisions that we can approach 0. We can get it probably really, really, really close to 0, but we're never quite going to get there because there's still air trapped in there. Okay. So now let's think about our balloon or the syringe, and I put it in the freezer, and I tried to cool it down, and I got it down to 0 degrees. But this relationship between volume and temperature, do you think we can ever get that temperature or the volume? Let's say I have this balloon or a volume of gas, and I try to freeze it really, really, really cold, like negative 150 degrees or negative 200 degrees, do you think we can ever get down to
No.
0 in our volume? Why not?
We just can't.
Why not?
There's air in there?
Okay, why does that sound like the right answer? Why does it sound like we could never get down
Just
to
like
0?
volume can't go all the way down to 0 with the pressure.
Okay. Why not though?
Because there's air.
Because we have something?
Yeah.
Okay. So
Like the air.
So this idea of absolute 0 is the idea that we're approaching getting the volume or the temperature so cold that those molecules actually stop moving. And so we're going to approach that 0 volume. And if we did that in Celsius, we would get all the way down to like negative 273 right here. And our graph looks like this. And so a new scale is using a different, instead of Celsius, using Kelvin. And it's just the same graph except for shifted over 273. So you'll see right here where I had 0 for my Celsius, my freezer. As you're working through this, I want you to also think about volume and temperature, where you saw that relationship in your tanker or your can. Were you looking at any difference between temperature, any change in volume, and or any change in temperature, and how did that relate to volume?
Okay, so to change it to Kelvin, we just go this plus 123 or 273.
And so you're going to do that, so you'll get the temperature in both Celsius and Kelvin, and then you're going to look at the ratio of volume to temperature for each, both in Celsius and in Kelvin. You'll see how. Okay, so whenever the volume doubled, did the temperature double? What appears to be the difference between the Kelvin and the Celsius scale in this situation? Which one? How does that?
Figure out ratio.
Only Kelvin doubled in volume at the same time as temperature. The Celsius it doesn't.
So Kelvin is, when we use Kelvin, we see this very clear relationship between volume and temperature. We see that the slope of this line is always going to be the same, volume divided by temperature. So remember when we talked about ratio being a slope? Everybody remember that? Do you remember when we talked about ratios for slope, volume divided by temperature, or anything on a slope of a line? No?
No.
Okay.
Man, we're lost.
Yeah. So I just want you to think about, you'll see on the back of the paper, you'll be looking at some slopes of a line. But if you didn't have a graph of this and you saw that the slope was 1.78, what would you picture the graph to look like? It's a positive number. What direction would that line go?
Go up.
Yep, it would go up. So what can you tell me if that line is going up? What's the relationship between volume and temperature?
Positive.
It's a positive relationship, which means if I increase what?
Temperature. And then what was it? Volume? Yeah, then volume will. That one.
It will what? Increase, yep. So it's not like pressure and volume, right?
No medium.
Try to figure out the ratio of volume
Balloon.
to temperature. So let's look at that balloon. How are you going to figure out the ratio of volume to temperature?
Don't we just divide? No, multiply volume.
Find two numbers.
Yep.
Yeah.
Okay, find 2 on there. Can you pick any 2? We're doing balloon A here.
Do this one here.
Okay.
Is that 300? No. This is 300. That's 250.
Okay, 250. And what's the volume?
400.
So what's the ratio of volume to temperature?
400 and 250.
400 what? 250. Times or divided by? We're finding a ratio. Yep. So you're going to divide it. Now, I have a question. Once he figures that out. What if I picked a point up here on the, what if I wanted to do this point?
You can't.
I can or can't?
Can't.
Why not?
Because I said so.
Okay. But what if I did? Would I get the same number that he just got?
Yeah.
Why?
You should, because it's straight line.
No.
No. It's not a straight line.
It's
Not
not?
linear.
What do you mean it's not linear?
I don't know.
What do you mean by linear?
Wait, you did.
1.6.
Okay, so he got 1.6. So you said yes, it should be the same, then you changed your mind. So why don't you test one other number on there and see if it's going to be the same?
Alright, so.
Here. 550
An 850.
Is that
850
850?
and 550.
Yep. Finish it tonight for homework.
1.5.
So it's close.
So it's close? Do you think you got it exactly right on? Is that number right on that point there? Look closely. Is it right on there?
No.
Okay. So do you think that the ratio is always the same for the
Yeah,
line?
it's always
So you were right. Because it's a line, the slope of that line is the ratio.
Yep.
So the slope of this line is 1.6 because you did volume divided by temperature. Finish this tonight.
Exactly at what temperature?
Oh.
Another temperature.
So you have to kind of guess. Well, you can just guess. That's fine.
So like there's when it's done and then like a second and then the rest of it's done.
Okay.
Just gonna do it one.
What will happen is the tire will walk.
Decrease? Why? Yeah.
Or no.
Why?
This dentist did this.
So what did that do? Why?
Like,
And so what does that do to the molecules?
and she's like, what?
And then what does that do?
She's like,
Okay, so let's go ahead and get started. Let's talk about our tire here. What's going to happen to our tire?
Absolutely nothing.
Hey, those are nice rims. The volume is going to increase.
The volume is going to increase. Why?
Because temperature got higher, so then the tire will expand because of the molecules moving back and pushing on the wall.
Okay, so Byron just told us a bunch of things there, so let's everybody listen to what he's had to say and see if you agree or not agree. So can you say it again, please?
Volume is going to increase because the temperature got higher, so therefore the tire is going to expand because the molecules moving fast and they're pushing on the walls of the tire.
Okay, good. Does everybody agree?
No.
Does anybody have something to add to that? Okay, so he explained that he thinks those molecules are moving around more and that the pressure also increased. So, but that increases the volume because it's pushing out against it. So yesterday you looked at two different balloons and we were graphing volume versus temperature. So on these two graphs, it asks you to pick a point and calculate the ratio of volume to temperature. And so you maybe picked a point on container A, and you calculated the ratio of volume to temperature. So can somebody tell me the ratio you found here and how you found it?
1.7.
Okay. How did you find it? So she picked this point. What if I picked a point like right here? Is the ratio going, like what's going to happen to the ratio? It's going to be the same? How do you know it's going to be the same? Because this line is increasing. What? I need a little more volume. Okay.
Because if you look at this, like if you double 150 to 300, wait, if you double 200 to 400, it's almost double.
Okay, so if you double from 200 to 400, it's almost double. So it's going up at this constant slope, right? So we have the slope of the line, which should be this number, 1.6. So every number on that line, if you do volume divided by temperature, should be the same. Same for container B. And what's good about using Kelvin is that these should always continue straight down through the origin, through 0, 0. Okay, so we have this equation that we can use to describe volume and temperature. Okay, so this is called Charles' law. You might want to jot this down in your notes section. Charles' law is this idea that for a given mass, the volume is directly proportional to the temperature in Kelvin. So it's not indirectly proportional. It doesn't go this way. It goes this way. So this would be indirectly proportional. This is directly proportional. They both increase. I think it can be written both ways. So our same car has 11 liters of air in its tire and it's 0 degrees outside. Later that day, the temperature has increased to 26 degrees Celsius. So now you're going to calculate the new volume of the air in the tire. So go ahead and take a couple minutes with the person next to you, try to figure that out. What's the new volume of air in that tire? So my initial volume, what's my initial volume of my car tire?
11 liters.
So we have 11 liters. And what's my initial temperature?
0.
Oh,
270.
what?
So is it 0?
270.
No.
I can't divide by 0.
No.
So I'm going to convert that to Kelvin, which is 0 plus 273, which is 273. And now we're going to say, what's our second volume? That's what we're solving for. So you could either put V2 again, or you could put yourself an X. And what's our second temperature? Is it 26?
299.
299. We had to add 273 to 26 to get our temperature in Kelvin. So now we have 11 over 273 equals X over 299. So how would you solve for X now? Cross multiply, so you could do 11 times 299 equals 273 times X.
Would dividing work?
You could also just divide 11 divided by 273 equals X over 299 and then multiply. So either way that you know that you like to solve for this, solve for X for me now that we have this equation. But you should have gotten something around 12 liters. So think back to what you answered for the entry question. Did we get the result that you expected? So what happened to the volume in the tire? It increased. It went from 11 liters and now it's 12 liters. And I saw some of you writing in your entry question another way besides just the air temperature going up outside. You said that another way that the temperature of the tire could increase. Who wrote something about that? Was it you? How did you said something about the temperature increasing in the tire because of being on the road?
The cement's more hotter than mine.
Okay, so being on the cement also could increase the air of your tire. And how about driving along?
Yeah.
Friction could cause some heat increase too. So there's lots of ways that you can get a temperature increase in your tire. So now we've done volume and temperature here. So volume and temperature. So fill in what you know about volume and temperature now. So the last relationship we're going to look at today is pressure and temperature. So we're going to combine pressure and temperature. What do you already know about pressure and temperature? How do you think they might be related? Tell somebody next to you. Okay, so what do we all think about pressure and temperature? How are they related?
Yup.
I think that they're going to be inversely.
Okay, so you think, let's listen to what other people have to say, please. She thinks they're going to be inversely proportional. Fabian, what do you think about that? She thinks that if I have temperature and pressure, they're going to be inversely proportional, so it'll look like this. Tell me why.
Because, like, if the temperature increases, the volume's going to increase, and because volume and pressure are inversely proportional, when the volume goes up, the pressure's going to go down.
Okay, so, yeah, and what do you think?
But then the temperature, makes the molecules move faster, causing more pressure.
Causing more pressure?
Yeah.
So what do you think the graph would look like?
I don't know.
If I have temperature and pressure, you think it'll go which way? This way? Okay, so we have two options here. We have, if we increase the temperature, it's going to make the volume increase, which is going to make the pressure decrease. So she thinks it looks like this. Or just, we have molecules moving around more quickly, which makes the pressure increase. And so, how about if I add this piece to it? We're going to keep, remember how we kept the pressure the same here? For our relationship between pressure and temperature, we're going to say the volume doesn't change. It's a fixed or unchangeable volume. So like a container where you can't change the volume, what do you think is going to happen if I increase the temperature?
It'll be direction.
So tell somebody what you think about that now if we say the container has to not, it can't change volume. So now, we can't change the volume of the container, but I'm going to increase the temperature. What will happen to the pressure? It'll what? Increase?
What Ricardo, the pressure will increase?
No,
Can you expand more on that?
Right, sure.
But you think it'll increase?
Calculated, right?
Okay, so that is true. It will increase if,
Right.
like how Justin said, if the molecules are moving around more quickly and they're trapped in the same size of container, then that pressure will increase. So I want you to think about this. Okay, so you start at sea level, and the pressure is 1 atmosphere. That's our normal atmosphere pressure here. Suppose you climb up a high mountain where the pressure is lower. The pressure went down when we went up our mountain to 0.75. And let's say the temperature didn't change. And you have a bag of potato chips and you have a glass bottle of soda. Does the pressure inside your unopened bag of potato chips change? And does the pressure inside your unopened glass bottle of soda change?
No and no.
So decide that with people around you. Does the pressure inside your potato chips bag change? And does the pressure inside your soda bottle change? What's going to happen to that bag of potato chips as I go up that mountain?
It will stay somewhat.
The side will stay the same, but it'll seem to expand.
Okay, so tell me more about that. Let's listen to Colin, please.
The pressure outside is different, so it can expand more than it usually is.
Okay, so we have our bag of potato chips here. It's squishable.
And they're spicy nacho Doritos.
Okay, they're spicy nacho Doritos. And what else do we have? We have air molecules inside of our bag here.
Here, Brenda.
Yeah, because they only give you half a bag of chips.
And we have air molecules outside of our bag here.
Nothing happens.
Okay, now I go up the mountain where the pressure outside is lower. So what's going to happen to our bag?
Oh, it's gonna get lower.
Expand.
What's going to get lower?
The pressure in the bag.
The pressure in the bag will get lower.
It'll like.
Hold up.
So it open.
You start out
So
with the
it's higher.
pressure. Wait, I'm so confused right now.
I don't know.
So what's confusing?
It's gonna get higher.
The temperature doesn't change at all.
The temperature's not changing.
Yeah.
So we just have a bag of chips, and we went up the mountain, and what did I change in this situation here?
Pressure.
The pressure outside.
Lower.
Okay, so I made the pressure outside lower, Carson. So what's going to happen inside the bag?
The bag might expand.
The bag might expand. Why?
Because there's less pressure on the bag.
Because
Okay.
the pressure's not equal. Like the pressure outside decreased, or like the pressure inside still the same, and it's still pushing out.
Okay, so we have an unequal pressure now, and so what does the bag of chips do kind of in response to that to equalize the pressures?
Yeah, a little bit.
Bag.
Volume
Expand.
So the volume increases, and we now have equalized the pressures between the inside and the outside.
More chips.
And you maybe have seen that with a bag of chips before, like if it got a little bit kind of, have you seen chips before where the bag got a little bit more
When we were
expanded?
going to Oregon up the mountain, our bag was like,
Yeah, so you've seen this happen before where you went up a mountain and your bag of chips like got big.
exploded. It was like a pillow.
It did explode or almost did?
Almost.
Okay. And then your unopened glass
Open it,
of
looks like.
soda. So same thing, we have our little soda bottle here.
Heck no,
That
glass
I-
will not explode.
Can't really draw.
I mean,
Okay.
not like,
So we have our glass of, it's like our glass bottle here.
this is insane.
And we have air pressure outside. We have air pressure inside.
Yeah.
Where's the air in a,
On the top.
Right at the top.
At the mirror top.
There's just air at the top in soda?
No.
Where else is there air?
In the soda itself.
Okay. So we have in soda, we have air molecules that are dissolved, that carbon dioxide, into the pot. Okay, so they're also putting pressure against here. Now I'm going up the mountain. What's going to happen?
Nothing.
What do you mean nothing?
It's glass.
You're gonna crack.
Okay, so the glass, what do you know about glass? What does
Too
glass...
much pressure on it, it explodes.
It's just solid.
It doesn't expand.
Okay.
Shatters.
So the glass bottle itself cannot expand. Okay. Imagine that is the glass bottle. So it can't expand, so then the pressure outside is less. So what happens to the pressure inside?
It's just gonna increase.
So the pressure increases inside here. And the volume is fixed. The volume can't change, so we get an increase in pressure inside of this bottle.
And then when you open it, you're gonna get like a little sample.
Yep, that's what Tanya was explaining too. Like you open that bottle up the mountain, you expected it to kind of totally fizz all out over the place because we had such a high increase in the pressure inside that bottle.
When you shake it.
It's good thing air pumps are pressurized then.
Yeah.
All that stuff they have on there.
Yeah.
Okay, so this is the last thing today before you have some work time to think about these things. This relationship between pressure and temperature, like you just described, is directly proportional if we keep the volume constant. If we don't keep the volume constant, we can't describe it the same way. But if we're only looking at the relationship between temperature and pressure, we get the directly proportional relationship. All right, so pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. And you're going to practice that today. So the worksheet you picked up on your way in has 2 scenarios that you're going to look at. One scenario, I'll put that back up if you need it. One scenario is talking about gas in a container where the volume can change, a balloon or a tire or something where we can change the volume. And the second one is talking about a container that cannot change. So it's another example here of the glass bottle where the volume itself can't change. So we're just looking at the change in pressure. So we're changing pressure. What else are we changing, do you think?
Temperature?
Are we changing temperature?
Well, when you go up No.
Okay, so we didn't change the temperature. Often when we do go up a mountain, the temperature does change, but in this problem, it was a cold day down below, and it's still cold up above. So temperatures stayed the same, and what do you think is going to change? What else is going to change? So the volume might change? Okay, so that's what you're going to write here. Why do you think the volume might change? Because pressure changed? Okay. And how does pressure, why would volume change if you change the pressure?
We write it first.
Okay.
Yeah.
I'll let you do that.
Temperature will change pressure.
Temperature changes pressure. And does pressure, what about, but we're not changing temperature in this situation, so can pressure change volume if we increase the pressure? Okay. What happened when we changed the pressure in that on the syringe?
It was more volume.
When you did what with the pressure?
No, less volume.
When you did what?
When you push the thing.
So when you increase the pressure, you got less volume. And so let's think about this balloon. If we go up on the mountain with a balloon, and what are we doing with the pressure when we go up the mountain?
It's going to get smaller. Because the volume is going to decrease.
Well, what happens to the pressure when we go up on the mountain?
Oh, it gets higher.
What increases? When you go up the mountain, the air pressure increases.
No, decreases. I don't know.
Okay, so let's read the problem. What happens to the air pressure? So the air pressure decreases when you go up the mountain. So what do you think will happen to the volume if you decrease the pressure?
It's gonna get higher.
Yep, it'll increase. So we're going to see, you're going to end up calculating that, but you're going to expect that your balloon would increase if you go up a mountain, just like our bag of potato chips. Right?